Everyone, welcome to the webinar of Thermal Energy HQ. Today is the first time we are holding this webinar under our new brand name, Thermal Energy HQ. You may know us as PowerPanel. We are going to cover a couple of points today. We want to introduce you to our products, introduce you to our team, and share with you the benefits that you can obtain in working with Thermal Energy HQ. First off, I'd like to introduce you to our CEO, Rob Kornarens. He will say a couple of words.
Thanks, everybody, and thanks for joining. I'm really excited with our new brand. What we discovered when we invented, you'll hear from my partner, the inventor, Garth Schultz. He invented a power panel that makes hot water and electricity at the same time. But he also had the thought of storing that hot water and energy. So we always sold the tanks with the PVT panels. What we learned is that the tanks by themselves, along with other heating mechanisms, which we'll go into, is very, very good. So we want to be known as the thermal headquarters for thermal storage. And that's what you're going to learn about today. My background is commercial roofing. I grew up in Long Island. I worked for a roofing company through high school and college. My boss had me open a branch in Atlanta, Georgia in 1979. He had me move to Florida, take over an existing branch in 1982. And then I left in 1983 and borrowed $15,000 from my dad, bought a pickup truck, and started a commercial roofing company in Fort Lauderdale. And in 1994, we got into air conditioning and bought out a little air conditioning company because the air conditioning units were up on the roof, worked out well. In 2006, we saw solar coming on, photovoltaics. We started with a product called Unisolar. It was a thin film amorphous technology that would adhere fully to a PVC single ply roof. So we started Advanced Green Technologies in 2006. Today, we're the largest commercial roofing contractor in the state of Florida, as well as the largest commercial solar, as well as a small air conditioning division. I met my partner, Garth Schultz, about 12 years ago as I got into solar. He had invented PowerPanel along with the storage tanks and had just won some awards. So with him, we have grown this company to be a leader in PVT and now thermal storage. So you'll hear more from Garth later on the call. We also have Louise from our Puerto Rico office, Claire, she's handling the Virgin Islands as well as New York and other places. She's business development. Bill Arsenault is independent business development. And then we got Merrick, who handles website design, marketing, and press releases. So I'll turn it back over to Garth and give a little bit of his background, and then Oliver can tell you about his background, and then we'll get a nice education on the best thermal battery in the world. So go ahead, Garth.
Oh, thanks. Good afternoon, everyone. My name is Garth Schultz, inventor of the products that we'll see on screen today. But that invention is one thing, and then the team that we've put together to bring it to market, they'll introduce themselves and you'll become aware of just what a great opportunity it is for you to use our product to its fullest extent for energy efficiency and recapture and renewable energy generation. My background as an automotive engineer, I'm originally from Canada. I spent 25 years here in Detroit doing full vehicle engineering work, usually hot rods and other creations, and worked in the kind of the craft industry, small volume production. Came across renewables, started to audit and think about it in 2005 after Hurricane Katrina. And as a result, saw what was happening out in the solar industry and put a couple of prototypes together of a very crude PVT module. Took that off to Next Energy in downtown Detroit, the New Center area, and they gave me a grant to come in and develop out our product set. And in addition to the PVT, the thermal storage tank came along because we needed tanks to go underneath the collectors. And as a result, we've put these out in systems in prototype in the PVT world, but also the coming wave of high efficiency air source heat pumps said there's an opportunity here for us to do something with the tank in that market. And additionally, we'll hear today about energy capture mechanisms, and we've got some new programs happening in Puerto Rico that utilize energy recapture and storing in our tanks. So we look forward to this afternoon and displaying what we have.
Thank you so much, Garth. A good outcome would be that we can keep your attention throughout this webinar. A better outcome would be that not only do we keep your attention, but you start to think about who else could benefit from this. And the best outcome, frankly, is if you start to think about specific projects, situations where you can leverage this technology, pick up the phone or send an email, and we can begin the dialogue. So let me give a very brief summary of what you're going to hear today. So what's the point? First, we have a highly innovative solution to expand your thermal storage ability, the thermal tank. And you need to really forget everything you think you know about thermal storage tanks. This is unique. This is different, custom designed for flexibility, high performance, and durability. So we'll go into a lot of detail on the thermal tank. Number two, this tank does not care where the energy comes from. It can come from heat pumps, from our patented solar PVT array, from waste energy sources, or even from existing energy inputs. And we will cover these various energy sources and how they work with a tank. The result of that are compelling economic outcomes. For the majority of our client, it is about the economics, the return on investment, the payback period, the net savings. There are some additional considerations in decarbonization, the ability to obtain specific loans through programs that value green energies, a reputational benefit of moving with alternative energies. But at the end of the day, we want to talk about how we will help you and your clients improve the economics of a project. So we're going to dive in first, exploring the tank in more detail, our innovative storage solution. And Garth, I'm going to call on you. This is your invention. There's nobody better than you to walk us through that. So we'll start with the design. Tell us a little bit about why you created it in this manner. How did this come about? And what advantages come with this design?
Thank you. Walk it in, walk it through. That was the design motivation for us. The lab that I was in downtown Detroit, one single door, hard to get into. I had a big PVT array up on the rooftop. I wanted thermal storage in my lab and couldn't get a normal tank in there. And the person that was supposed to deliver a thermal storage tank never showed up. So this resulted from need. And with that and background in automotive and plastics and foams that we applied to the structure, some of it came from the roofing industry too. But easily to move into a space where you couldn't think you could put thermal storage, and then that was the result. And certain patents have come up for us, but an easy to install unit.
And we had an example, a consideration in Old Town San Juan, Puerto Rico, very narrow roads. If you wanted to lift a steel tank onto a roof of a hotel there, you'd have to block the road, bring a crane into there if you can even fit it in. And in our case, you could take the individual pieces, bring them up the elevator, no hassle at all. There's more to the design. Let's go into the individual components that make up that tank, and they have a common theme, which is durability. Talk a little bit more about that.
Correct. So starting with the base element of a tank is the insulation. One thinks of a thermal tank, and you've got to keep that energy in there. So our base insulator is made from expanded polypropylene foam, commonly used in automotive industry, but other industrial processes as well. And it's highly insulative, easy, and it's a one-part steam chest. So it's at the end of its life, which is a long time, it can be fully recaptured and reclaimed. Outer protection and what contains the fluid pressure is a hoop made out of thermoplastic olefin, roofing material. And we utilize that in an 80 mil thickness in order to provide our structure. And then lining and containing the fluid is a high temperature PVC liner set. And then we cap it off with a unique top assembly, and everything dresses from the top so that you can put in heat exchangers, pumps, sensors, and it's all dressed from the top. And we can customize those lid assemblies for your particular heat exchanger, pump, and or sensor needs.
All right, excellent. Another design element that people often sort of understand on the second take is that this is not really a tank, but it operates as a as a thermal battery with a working fluid. Explain that concept a little bit to us. What's the difference between the water in the tank and the water that is being heated?
Yeah. And you always come up with a very good description of it. The water in the tank is our working fluid. It's not what you take a shower with or what you use in your process. And we use this, just standard water set. And then we'll either use a direct pump into devices such as the air to liquid heat pump shown on the screen, and or an immersive heat exchanger set, and or an active heat exchanger set in order to exchange fluid from the working fluid that's stored in the tank to the processes that you're addressing.
And this is very different from the traditional steel tanks where the water goes in, it is heated in the tank, and then it comes out as hot water. And with that, new minerals are constantly being introduced to the tank. And I think you gave a story how you had to deinstall one of these tanks once, and you compared it to gutting a whale with all the stuff that was coming out. What is the risk of mineral deposits or any kind of deposits in this tank?
It's minimal. Ideally, it's a one-time fill of the tank. There might be some evaporation loss over the years, and we address that by putting a monitor in there that tells you what the fluid level is in the tank. But really, it's a one-time fill of that working fluid that goes out to your particular device and is the storage media. So it's a one-time fill. Anything that's has a continual mineral load in it, it's passing through the heat exchanger systems, and that allows you don't have to bother removing sediment from the bottom of a tank as you would with a standard pressurized vessel.
So I got a question recently where somebody said, well, wait a minute. So you basically have a bathtub full of hot water and you're guiding my cold water through there and it comes out as hot water. How is that possible? Let's talk a little bit about the heat exchanger. You see it in the image on the right-hand side. You and I just had a more detailed conversation the other day. Tell us more about this nylon heat exchanger. And in particular, the surface area of this heat exchanger.
Thank you. In a common, our smallest tank that we have to market today, a 350-gallon unit, we use an immersive heat exchanger assembly made by a company up in Canada, all nylon polymeric construction. That means it's not going to degrade in that water, and the process water you're putting through it isn't going to go and affect that heat exchanger. And that's a particular importance for us when you're out in market with RO waters that are very aggressive in environments to look at any metal, even stainless steel, that they can get attracted to and start to pit that. With the nylon heat exchanger assembly, and someone thinks, well, nylon won't work, but if you lay this design out, it's got large surface area, and for our applications for domestic hot water systems, where there's an RO or potential for corrosion, we address that. But we're kind of heat exchanger agnostic. If you got a good coil loop assembly, copper, stainless steel that fits your application, we have designs on that, or we'll assist you in the design of the heat exchanger that meets your needs.
And I recall one number that really blew me away when you had calculated that the surface area of this nylon heat exchanger is 95 square feet. That's more than the internal area of the entire tank. So that's really impressive.
Yeah, clever people that we purchased that, design from. And it started out as a DuPont exercise so they could sell nylon into the automotive industry. And then they rolled that company off to a firm in Canada called Cesaroni that manufactures those for replacement heat exchanger sets in cooling towers and wherever corrosion is prevalent in an HVAC and or process fluid situation.
So talk a little bit about the temperatures. What are typical temperatures of the working fluid? And then as a result of that, what are some of the maximum output temperatures that we can accomplish?
Yeah, domestic hot water, 120 degrees Fahrenheit, 50 degrees Celsius. That's kind of what your hot water heater, domestic hot water systems are set at. Out of your tap, you're at 42, Celsius, but we can build temperature all the way to 200 degrees Fahrenheit, 90 degrees Celsius in that tank. And then on the lower end, if you want to use the tank as a buffering system for chilled water, you can go down to 40 degrees Fahrenheit as those processes demand. So it's universal in terms of what temperature you store at, and as the designer of the heat exchanger or of the system, you can spec where is it that my device can recapture and store at, and what's the best utilization within my process.
All right. We also have a growth journey. When I first joined the company, there was one 350-gallon tank. We now have 3, with more on the roadmap. Talk a little bit about the advantages or the different segments that can benefit from smaller tanks and larger tanks. What are some of the considerations there?
Well, number one, the real estate. Where am I going to go put this thermal storage system? And aside from the capability of being able to walk the parts into that boiler room or locate outside on a rooftop, we've built up structures from 700, 500, and 350 gallon on a common 5-foot, 60-inch diameter footprint, so that we can match your space needs and your space utilization. If you have all the space in the world and you need large thermal storage, then the 700-gallon tank will work. And then we also have capability of chaining these, joining them fluidically together in order to give you expanded capacity. So 700, 1400, 2100 gallons, 28, we can go on in order to match your energy storage needs.
And then we see the little illustration. So the 700-gallon tank is quite tall. What kind of a ceiling height would you need in your mechanical room to fit that in?
For giving you working space, we're a little bit above 7 feet on the 700-gallon tank. And if you had a 9.5-foot mechanical room, that allows you room to assemble and put the tank into place. The way that assembly of that larger tank is, the sidewall segments come in separately, so you're not having to load into where you crash the ceiling in order to get the parts into place.
All right. So quick recap: design for easy install, design for durability, and design for performance. Now let's talk about how this tank pairs with various energy inputs. In traditional system of water heating, you either typically burn gas or maybe light oil, or you have an electric water heater. All of these are expensive sources of energy. So we're going to talk primarily about leveraged energies, but we will also demonstrate that it can work with traditional forms of energy. The first example we have is thermal tank plus heat pump. We have a partner company in California that sources the heat pumps for us. These are monoblock high-performing heat pumps. And with that partnership also comes access to a very powerful control system. We will be talking more about that allows the control of the run times of the heat pump in response to rate cycles, in response to temperature in the system. So Garth, from an engineering perspective, how would you sort of characterize that partnership between the heat pump and the thermal tank?
Well, it's an ideal setup to maximize the capabilities of both the technologies. On the heat pump side, it's if you think of those devices, they're like the little engine that could. So you look at them and you go, there's no way that something that's putting out 26 kilowatts, on the bigger size one, or down to a small sized unit of 3.5 kilowatts, can build enough thermal potential in order to satisfy needs. And that's where the idea of the storage tank comes in, because then you can take that flexible storage platform that we have and build in that capacity, so that the heat pump, when it has the opportunity for demand charge reduction or time of use optimization to run, give you that full thermal charge so that you can utilize it when energy is expensive and or when the need applies from demands within your process.
Right. And so the art is really in the sizing, right? Figuring out what are the demands over the course of the day, even over the course of the year, when do the peak demands occur? And then pairing that with the rate cycle. So if you could run the heat pump all night long at a very low cost, you do need enough thermal storage capacity to put that heat somewhere, right? If you have a small tank, the heat pump will simply heat it up and then it's done. And if that water gets used in the morning, the heat pump has to run again during a high rate cycle, high cost rate cycle, right? So that's the dynamic that we're looking for here. What do you need on the storage capacity, and what do you need on the energy generation capacity? For those who are not so familiar with time of use optimization and demand charge, Garth, can you briefly explain? I think we've covered time of use, that's the different rate cycles, but what is a demand charge reduction? How does that play in here?
So the utility companies, in the way that they bill you today, there's going to be for consumption, that's one charge on your bill, and the other one is a demand, where they've added up all the loads of your that they see, and they'll usually go and pull your meter when these things will be peaking, and they say that is your demand charge of your system. And so if your incumbent systems came on and were part of that demand charge schedule, you're going to be dinged on your bill for that usage. What you benefit from using a heat pump and thermal storage is that you can run the system when those demand charges are not going to appear in the system. And additionally, as being a device that takes 1 watt of electricity and turns it into 3.5 or 4 parts worth of thermal energy, then in your system, you've reduced that overall demand in your load if you came from just resistive electric heaters.
So we essentially have a triple economic benefit here. Number one, we reduce the net energy inputs through the COP, right? The heat pump draws in ambient energy from the environment and has that leverage. So you need less energy that you pay for. Number two, we avoid high rate cycles. And number three, we avoid in some markets that extra charge that occurs for the peak rate that you achieved at some point in the month just by avoiding running your hot water system during that peak period. All right. This is an example how the tank and the heat pump work in conjunction with an existing system. Garth, can you give an example where such a setup makes sense, either from a legacy perspective or there is a need that does require that additional water boiler?
Correct. If your legacy system, if you've replaced it recently, you said, I've got a good natural gas hot water heating system in place, and it's not gonna, I don't want to take it out of commission. And or if you have peak loads where you say, I need that fossil fuel device in order to meet some demands that happen within your consumption schedule. And what we do is we place the thermal storage tank and the heat pump prior to that, and give that incumbent system all the preheat. And in normal operation, that's the incumbent system isn't going to turn on, and the thermal energy we pass on just passes through the system. But if you need a peak load to be met, then your incumbent system that you have in place will satisfy that.
And I recall we had a conversation with a very reputable engineering firm, and the lead engineer had brought up a drawing where he had 4 boilers and 4 heat pumps and a small buffer in between. And he immediately saw the opportunity by just expanding the storage. He could save at least one out of the 4 boilers and one or multiple of the heat pumps. So even the net system investment came down by inserting the thermal tank as a buffer storage there. All right, let's talk about no energy leverage in the sense that we've talked about right now. We don't have a heat pump in this example, but there is still a benefit to having a thermal tank sitting behind an indirect hot water heater. How does that come about?
If your incumbent system, and there's various examples that we see on instant or tankless hot water systems where they just can't meet the demand at the time that the customer wants that that thermal energy. So you can take a smaller indirect hot water heater, cycle it, use our thermal storage battery, and build the potential within the tank so that when those peak needs are required, the system can respond to it adequately and without leaving the customer or the client, without their process heat being achieved.
So say you had a hotel and your hot water heater could reliably serve 10 rooms, but maybe you have 15 rooms, the hotel grew over time. Instead of having to add another water heater and have that high energy consumption, in that case, you just basically run it at night, same benefits, time of use, optimization, and the storage tank provides you that capacity that everyone gets a hot shower in the morning. All right. Now, this is another key invention. In fact, the original name of the company was PowerPanel, named after this invention. Talk a little bit about photovoltaic thermal and what the benefits are in this system that a heat pump alone cannot cover.
Well, the idea of a complete renewable system that can maximize the energy capture from the sun. So a typical PV module, and they're very good, and they produce electricity 25% efficient. A good thermal module, glazed module of old and still current in market, they 75-80% peak efficiency. So the idea was combine the two and give the customer or the client the best of both worlds. One, electricity, and two, thermal that's captured. And the thermal that's captured actually enhances the efficiency of the PV because that thermal capture actually cools those cells on peak days, peak solar days.
The rendering on the bottom is from an actual install, Bolongo Bay in the Virgin Islands. Talk a little bit about the story of that install.
So Bolongo Bay Beach Resort, they had an older solar thermal system with a multiple of tanks that had cycled or were not longer functional. And really the hot water system was unusable. So anyone in the four wings of the hotel, 45 rooms that they were servicing, woke up and whatever water was in there was the water you're showering. The opportunity came, one, on the baseline to replace that system, and that's where on that lower level you see two tanks and a heat pump installed. So we designed and spec'd that. And then on the rooftop, in order to supplement and power balance out the electrical energy used by the heat pump, we put in our PVT system and also supplied preheated water that goes into that baseline system. So the two marry and work together. On good sunny days down in the Caribbean, the heat pump runs very little, and then all the energy for showering cycles through the tanks that are associated with the heat pump, but the heat pump doesn't turn on. And then at high demand periods or if you're get a series of cloudy hurricane weather kind of days, then the heat pump takes over and supplies that baseline energy. So it's a perfect marriage of the two technologies, all coupled together with our thermal storage system. So we maximize thermal storage so that at nighttime and off days of solar, the client is supplied.
You mentioned hurricanes. We hear from many clients in the Caribbean in particular that the power grid is not always reliable. So that term of grid independence, can I operate my hotel? Can I operate my hospital without having to turn on the generator, which is even more expensive than the typical energy? How close can a system like this come to grid independence, at least as it pertains to hot water?
Oh, yeah, by our energy balance, 100% of the thermal energy on the domestic hot water situation can be covered and coupled, by the heat pump and the PVT module working in concert with one another. So there is no need. And the net energy, electricity into the system is just that's utilized by the heat pump is produced by the PVT system.
Okay, excellent. The other consideration we talked earlier, heat pump and tank, there's a sizing art. How much flexibility is there to size this PVT solution?
Yeah, kind of the standard building block. That's 20 modules that you see pictured in front of you, and then we can build out that capacity, based upon your needs and your use. Underneath that particular array, we have 2,700 liters, 700 gallons worth of storage. If you have processes where you go, I want the PVT, but I instantly use all that energy up in my process in the building, the thermal storage element would become smaller. If you had processes in there, we go, I have, let's say in the case of an industrial laundry, you have no use during the weekends because you don't have people in there cycling that out. You have a PVT system in place. You want to maximize storage so that when they come back on Monday, the sun that came out on Saturday and Sunday is put to use on Monday.
So some of our clients have asked or have commented that they love the idea. They would love to have one of these on the roof, but they're not sure that the roof can handle the weight of those tanks, right, once they're filled with water. Do the tanks have to be immediately by the PVT, or are there other options?
No, we've mounted tanks in crawl spaces in basements and on the sides of buildings and in on the floors below. So the thermal storage element can be located in a multitude of locations relative to the generation facilities.
How much distance in terms of how many stories up and down, or how far can the tanks be removed from the PVT without losing really material functionality?
The one that we've done with the most space is we've done 3 floors, but you can even go more, just depending on what pump is spec'd with the tank to move the fluid up, the working fluid up into the collectors. So you can size, where you locate the tank relative to the collection system. That's just a matter of pump power in order to supply. But ideally, in order to minimize pump power, you want to couple those things, close together so that you maximize the COP of the system itself.
All right. Now you have a patent on this water cascade, which is really sort of the secret of converting a PV into a PVT. Explain a little bit more how this works and what some of the benefits are of having this drain back system.
So what you see in front of you with the curious gray cascading parts, that is the fluid as it would pass underneath what we call our PV insert, which is our absorber sheet in a solar thermal module. In us, we use that solar thermal module and we build PV onto it. So that film of water passes through, it comes in through the top. This is a drain back system, and in contact with the backside of the absorber, cascades down through the module, taking that heat away. The other important thing about the design and the patents on this is that that's an equal distribution across that absorber plate, which is highly important to PV because you never want a hotspot PV cell. It provides an even cooling effect to the PV, which makes the PV last longer.
So when you go into some Caribbean countries, you see the traditional thermal siphons up on the roof. They make hot water, but the key difference there is that the hot water stays in them, and that is why they can only be installed in frost-free climates. What would happen here on a frosty or snowy day if you had this up on your roof?
Well, there's no water in it. So when it says when the control system that we have says by construction, we're called a drain back system. So all the working fluid belongs in the tank, and it's only when the temperature differential on the module or that through a maintenance cycle that you call the pump to engage, that water's put up into the collectors. And because it's a drain back, and the unique design of the collector is that it's vented to atmosphere, and so it's very friendly to have water as a working fluid, even in the latitude that I'm in Michigan, and you can think over in New York State and all across the Midwest, this collector was designed for that environment.
Mm-hmm. All right. So we've covered solar energy as a source of input. We had previously covered ambient energy, the energy in the environment. Let's talk about waste energy. I recall us being at a high-end resort in the Caribbean, and we're looking for a place to put the tank, and right next to us is one of the big chiller units, and it's just blowing out hot air, right? And so the thought was, what about that energy? How could we utilize that energy? And that's the first time I heard about the concept of a desuperheater. So talk a little bit about this idea of taking energy that would otherwise be wasted and the various forms in which that can be captured.
So in a refrigeration cycle associated with the chiller, and you can call this, you can add in a mechanism just after the compressor output called partial heat recovery. People call them desuperheaters, and it takes that hot refrigerant and then through a flat plate heat exchanger system allows you to go build thermal potential for use in processes, domestic hot water, or other uses in your facility. So it can be built in and spec'd as part of the chiller assembly, and you can also, there's systems out there that you can graft in as a kind of an aftermarket assembly as well. But your primary, in your best direction, is to have that spec'd in when your new chiller comes into place, and that'll give you cooler refrigerant temperatures so that your condenser side of your operation operates that much easier on your rooftop unit or your chiller.
And then on the right-hand side, we see one example of a wastewater heat recovery system. In breweries, in laundries, a lot of hot water goes down the drain, literally. And these systems allow a percentage of that waste energy to be recovered, put back in the tank as the storage medium, and then be used again. And that really changes the energy equation dramatically, because in this case, your incoming water is not going to come in at, whatever the ambient temperature is, say, 55 degrees Fahrenheit, but it might already come in at 99 degrees Fahrenheit. So a heat pump or whatever other heat source you have that sits on the back end of that has far less work to do to get it to the target temperature where it re-enters the process. We've talked about hot water, and you mentioned earlier it can also work on the cooling side. So give an example how somebody would utilize a tank full of cold water. What are some sample applications for that?
Well, the obvious one is space cooling. So most of the processes, if you don't have just an air-to-air air conditioning system, you're going to be running a chiller. The chiller makes chilled water. Chilled water gives you the opportunity to run the device at times a day, like the time of use that we described, if you have that buffering in the system. And additionally, the buffering in the system allows the heat pump or the chiller that's operating and the air handling unit, it gives buffering so that you don't short cycle the system, where the chiller turns on, turns off in demand to what's happening in the building. So it lengthens that on time, which is the hardest part of running a refrigeration system, is the startup needs of that. So the more consistently and longer time you can operate that by having buffering or storage in the system, that benefits the system the most.
Now, in this example here, we basically see the heat pump pushing out hot air, right? That's how it cools the water in the tank. In the previous example of heating the water, the heat pump was sucking in warm air from the environment. But we've also talked about actually combining a hot tank with a cold tank and putting a water-to-water heat pump in between. Can you elaborate a little bit on that? How does that work?
Yeah, so if you can picture two tanks, one where your hot fluid wants to be and the other one where your cold fluid wants to be, and sitting in between that is a liquid-to-liquid heat pump. So depending on what your process is doing, let's say you want to make chilled water, you're going to push the energy flow is going to come out of the building into the buffer tank, in through the liquid heat exchanger that's extracting that heat and then pushing it into the hot tank. The hot tank, in turn, gives you the opportunity, one, to utilize it in other processes in your building, such as a water preheat system, so that you can, that energy that would otherwise just get cascaded out into the atmosphere, you've reutilized in your process.
So if you have a scenario where a consistent hot water need occurs in parallel with a consistent cooling need, you can get optimal energy leverage, essentially.
Correct.
All right, excellent. Let's talk about the economic outcomes. There are multiple layers that you can stack here. The first one is the question on how does this compare from an investment perspective compared to just going with a traditional system. We've run many simulations, proposals for clients, in some cases replacing a traditional, every apartment has its own water heater, in some cases replacing traditional central systems. And in most cases, we come out favorably, not only because the equipment itself is very affordable, but also it is eligible for an array of incentives. Can you talk a little bit about the different types of incentives that apply here in a purchase scenario?
So from the federal investment tax credit perspective, we're applicable for the 30% federal ITC. And because our systems are manufactured in the USA, they qualify for an additional 10% as a base. I think if you're in a disadvantaged community or tribal scenario, you get another 10% that's applicable from the federal side. And then a la carte, you start to look at avoidance of penalties, such as Local Law 97, where they said if you don't decarbonize, get off of gas and move to an electrified source, there's that penalty that comes up, and that's saying adopt a heat pump. And if you do that, you need buffering, storage, of which we can supply. And then the local state incentives and or federal incentives for adoption of heat pumps would apply as well.
Now, one of the aspects that, there are different philosophies about how you recognize that in a cost-benefit calculation is the life cycle, right? We believe our equipment has a 25 to 30-year lifespan. In fact, even if a part of the tank were to fail, you simply replace that tank. You don't have to throw out the entire tank. And so our lifespan could be easily 2 to 3x that of a traditional steel tank. And so when you factor that into your investment equation, that you're not going to have to reinvest in replacement equipment, that obviously tilts the scale even more so. And then an added benefit is the reduced cost and complexity of the installation. From an operating cost perspective, the second level, we have talked about the reduced energy inputs, right? So less net electricity if you're replacing electric with heat pump. In the case of gas, it always comes down to how much are you paying for your gas. If you are in a market with very low natural gas prices, then it could be sort of a borderline consideration. Are you going to save money? At a minimum, you are going to move to a far more decarbonized model of operation. And we talked about markets like New York, California, Colorado. There's more and more states who are setting decarbonization incentives or are raising the prospect of penalties if people do not decarbonize. Garth, can you talk a little bit about maintenance? Because in any mechanical room, right, it's not a one-time build. You have to constantly maintain your equipment. How does our system compare to a traditional system from an annual maintenance perspective?
Well, it comes back to the initial fill of the working fluid water. For us, it's a one-time fill. So in a traditional boiler system, pressurized boiler system, where the water that you consume, that you use in your showers, that's a new mineral load that's coming into that device, every moment that it's utilized. And so that'll build and deposit. So there's a maintenance schedule for those traditional ones to drain those tanks and remove that mineral buildup. Calcium, it's for some people it's a white milky fluid that comes out, but that's destructive to the system and fouls heat exchanger systems. And for us, we avoid that. So that's an annual or biannual or whatever the maintenance schedule calls for avoidance that we apply. And then just on the replacement cycle, because we're all engineered plastics and foams, you're not having to worry about when does a steel cylinder need to get cycled out and replaced, and the planning for that, and then the expense of removing that after its life is over.
And another detail that I thought, I had not really considered that in the beginning, but when a traditional steel tank fails, it's usually some outlet on the bottom where the water starts to leak out. In our tank, there are no outlets on the bottom, right? You've designed it that all inputs and outputs are through the top of the tank. What's the advantage of that?
Space, and from a safety perspective, you don't have pumps and ground-mounted components to trip over that you would have on a traditional tank that has a lot of ins and outs coming in on the side at the place where the traditional boiler and hot water tanks have. Everything of ours is dressed from the top, and as we've pointed out earlier, you challenge us with what you want to put in the tank, and we'll design the top so that it all loads in for you and assembles.
Yeah. So it wasn't necessarily designed for aesthetics, but we've heard that concern from at least one client, and they said, look, that the tank, the surround of the tank can come in different colors. So you could even match it a little bit to the environment there, and it certainly looks a whole lot cleaner than a traditional tank with all the ins and outs, as you described, which nobody would ever consider even putting on the outside of a building. It usually belongs in the mechanical room.
Correct. Yeah. The design of the tank allows you to put it in many places, inside, outside, on rooftops, and the installation, the parts are easy to carry up and get into place.
All right, great. And then a final sort of add-on consideration is the appeal to customers. Customer satisfaction. We've seen case examples where the number one complaint on a review site for a hotel was the absence of hot water in the morning, and fixing that, addressing that, significantly increased the ratings for that hotel. And in fact, hot water consumption in that hotel went up by nearly 50% now that everybody could take a hot shower in the morning. And also the appeal to eco-conscious customers. We're working with an eco resort in Puerto Rico, and they specifically approached us with that idea. We want to be grid independent, and we want to have a very favorable eco balance, and our systems provide that. We have a variety of case studies. Time may not allow us to cover all of them, but at least I wanted to cover a few of them. The first one here is a very recent installation working with a design build firm in California, and they are always on the lookout for the next optimization. So they gave us a shot. The tank was installed, and you can see on the little picture here, the space in which that tank had to fit was really, really tight, right? So moving a massive equivalent steel tank in there would have been very challenging. And Garth, you've received some of the feedback from the people who installed that system and commissioned the system. What are you hearing in terms of their satisfaction?
We understand the client and mostly their clientele in that housing project are happy. There's no issues on hot water delivery, and the ability to it's an economical system for them, for these builders to adopt and move on to other projects that they do at the rate of one per week.
All right.
And it's also true, Garth, isn't it? I just heard yesterday that they're ordering tanks for 4 more jobs, that they switched over from boilers to drain back unpressurized systems, and the data that's coming out with our patented controls to control when peak expensive power is on, and we don't use that expensive. We use the off-grid pricing. Is working unbelievable. That they've had several engineers and architects out there testing it, and they just are ecstatic that it's exactly what we predicted it's doing.
Yeah. In fact, their acid test was to unplug the heat pump associated with the system, and then the storage volume says, can we make it through, a daily load, or a portion of the daily load with what's stored in the tank, and that came out as a good success for them as well. It says the heat exchanger sets inside of there and the tank volume that's specified work well for that client's usage profile.
Right. And that's a great illustration of the complex decision system. You have a client who may have never worked with a system like that. You have an engineering firm, a design firm, and then you have the installers, right? And everybody has maybe initial thoughts. I'd rather install what I'm familiar with. But once they see it, once they have that initial experience, there's almost no going back because the advantages that we've laid out in this webinar are quite overwhelming. A completely different example. This is a high-end resort. They have very powerful existing centralized infrastructure to both heat and cool water, but they have a very distributed campus, if you will, with multiple buildings, and they are running into some localized issues with hot water. So can you talk a little bit about the solution that we came up with here and how that supports their centralized system?
Yes. So if you can imagine 1.5 miles of a 4-inch diameter pipe that's carrying preheated water out to these 24 buildings and a spider web through each building, and when they're at maximum occupant load, they run out of hot water. So the solution set is on these buildings to put one of our tanks and a appropriate sized heat pump, and then take the load off of the main system by being able to supply through the heat pump and storage system that we're going to put into place. So it's a marvelous opportunity as this client builds out and they're going to a decarbonized infrastructure, that this becomes part of their solution set.
And so that the theme there is really to complement, right? Where the theme in the first one was to substitute a traditional system, here we are complementing a traditional system that just doesn't have the capacity to fulfill the needs any longer.
Correct.
All right. Laundry. We mentioned earlier, laundry, obviously a massive user of water. And depending on the type of machine, some machines heat the water internally, some need the water coming in hot already, especially on the commercial applications where cycle times matter. Talk a little bit about what's the benefit of installing a heat pump and tank in a laundry environment. And there are some sort of benefits that you might not think about initially.
So the primary one is that this particular laundries and industrial laundries in general, they use thousands upon thousands of gallons of hot water per day. And with that, and as Oliver pointed out, you think that's a modest economic return because they operate in propane and they have that arbitrage number, that number that the bigger the arbitrage is, the faster it pays back. But with the volume of water that they're using, it says the system does work and pay back. And then the secondary benefit I think you have noted on there is that the heat pump can be located on the interior of the building where all this heat is being rejected or generated from dryer systems, and then we can provide a space cooling effect so that you do it's a double win for the client, because in that you give them an air conditioned space, makes the workers more comfortable, and then also from a business case standpoint, it doubles the impact, because if you had to air condition that space, you get it for free.
Mm-hmm. And I believe you've designed a system for a brewery where you had a similar benefit, the tank essentially on the floor where the brewery need for hot water is, but the heat pump elevated at a call it a spectator gallery, cooling that space. Do I recall that correctly?
You sure do. And Claire is chasing that one down. It's Leatherback Brewing in St. Croix in the U.S. Virgin Islands. And then when we started to explain the thermal storage tank and then what the effect of the heat pump can be, and describing an air source, they said you can put this beside the picnic tables and where your clientele come to gather to view what's happening out in the brewery, and they want to stay there and drink more beer.
All right. We've talked about Bolongo Bay earlier, so thanks for covering that. Maybe one last one, because it's a little bit different. This is a PVT use case similar to Belongo Bay, but here the consideration of the client was not just pure economics, right? This was also about eco appeal. What stood out in this use case to you, Garth?
Well, it was the client himself. You know, you have options here to use heat pumps and storage tanks that kind of get hidden away in the boiler room where they do their work, or you can be the face of a responsible organization and say, look, we're putting renewables up, we have them, and it actually, that little bit of an array that's shown in that building supplies the domestic hot water into that particular unit. So, you know, the opportunity from a really high performing efficient PVT module is put to good use there, and then also, you know, coupled with energy storage from the tank.
All right. So we briefly wanted to introduce our team. You've heard already from Rob and Garth, and here is the rest of our team. Graham is our Chief Revenue Officer, is leading our sales team. I had the privilege of guiding you through today. Josh Plaisted is our partner on the heat pump and control system, and Marek is our marketing wizard. And you see Bill, Claire, and Louise, who are leading our sales efforts on the ground. Any of them would be more than happy to take your questions and work through specific situations that you have, whether it's a new project that you're designing, building a renovation, or a replacement of an existing system. We don't have any guests today, so there's not a Q&A section, but please do email us any questions you have. info@powerpanel.com or info@thermalenergyhq.com. Both work to receive your questions.
And then also, we have a small model replica that we could send you if you're a qualified buyer. That would show you exactly, it's 9 pieces, and it, you know, could sit on your desk, but it really shows you the way this thing goes and the ease of it. A lot of people tell me, wow, I've watched your video, I saw your brochure, but until I put my hands on it, I didn't realize what a great invention this is, and kudos for Garth for inventing the tank and the PVT. We also have other designs for a solar wind combination on a tracking, as well as other inventions like aquaponics called AquaGrow. So we're an innovative R&D company, but these are our main products. Right now, we're really getting the thermal energy headquarters really cranking and well received in all markets we've been into. So please stay tuned, sign up for our Instagram and other social media, follow us, and thank you for attending today.
Thank you. Bye-bye.
Thank you, everybody.